So the Black-Scholes formula is what? So if we look at a call formula, it's the present value of an expected payoff. Now G star is the log-normal probability density of ST, where we use R instead of alpha, right? Because we're using the risk-neutral probability distribution of stock prices. That's how Black-Scholes operates. We cannot use the alpha formula, so we'll put a little star there to remind us that we're using not the real-world distribution of S prices, but instead the risk-neutral, and all we have to do is just replace all of our alphas with R's, and it's just that simple. So the call is the present value of the expected payoff. The expectation is defined relative to the risk-neutral measure. So because an expectation can be split, I can write this as the expected value of S minus the expected value of K. Now note that I can write the expected value as a conditional times the probability of the condition. In other words, if I go back to the definition of the conditional probability function, it equals the original probability function divided by the probability of the condition. Here I'm just expressing that formula backwards. I'm saying the original probability function G star is the conditional times the probability of the condition. And I do that in both places. And now I go back and I use all the formulas we've developed. We've developed a formula for the conditional mean and the probability that S is big. This, of course, is easy. The conditional expectation of a constant is just a constant, and we have a formula for this. The formula, and so if we go back to the prior slide, we have developed a formula for the conditional mean that conditional on S is big, and if we just go back and recall it, the conditional mean of S when S is big is e to the S0 e to the R minus delta, and what we see is the R's cancel. So we only get left with here an e to the minus delta t, because the present value e to the minus RT cancels the positive e to the RT in the formula. And we have Black-Scholes. The n of D2 comes from this term, and the product of n of D2 in the earlier ratio comes from this one. And we can do precisely the same derivation for the put. Let's just run through it, and with two derivations we should feel pretty comfortable that this is a reasonably efficient way to derive this formula. So let's now derive the Black-Scholes formula for a put using the same approach. So the put is going to be the present value of the expected payoff for a put. So because we have a log-normal distribution of prices, we're going to integrate from 0 to k of k minus s, which is the payoff, and we're going to again use the notation G star of s to mean. This is the log-normal distribution of stock prices where we replace the alphas in the earlier formula with R. So I can, again, write this as a present value of e to the minus RT. I can split the integral as the integral from 0 to k of k, and then I have minus e to the RT times the integral from 0 to k of s. So what I see here is I can factor the k out. This is e to the minus RT times k. And what is the integral from 0 to k of G star? Well, it's simply the probability that s is less than k. And then I go over here, and This is e to the minus RT, and I'm going to use the same trick as the prior slide. This is not quite the expected value of S, because over the range from 0 to k, G star is not a probability function. So I have to write this as the expected value of S conditional on S being smaller than k, but then I have to multiply it by the probability that S is less than k. Same trick as before. The conditional probability function is the original divided by the probability of the condition, and here we're just multiplying it out. So now we're done. I get e to the minus RT k. The probability that S is less than k is n of minus d2. And then I have an e to the minus RT. We have a formula for the conditional expectation of S, and we got, it was e to the r minus delta t S0, and then we have a ratio n of minus d1 divided by n of minus d2, and then I have a multiplied by the probability of the condition, same condition, n of minus d2. So I have a cancellation and lots of cancellations, and I finally get, it's the present value of the strike times n of minus d2 minus, notice the e to the minus RT cancels out just as it did in the call formula, and I only end up with the present value in the dividend terms of S0 times the n of d2 cancels, n of d1. And there we have the Black-Scholes formula for a put, which comes directly from the observation that in both cases, puts and calls are the present value of the expected payoff, and what we need to do is remember the payoff is defined in terms, or the probabilities of payoffs are defined in the risk-neutral world, and develop the probability distribution, the conditional distribution, and we go through these formulas.